All right, we're going to get started. I'm pleased to introduce from the Xen Project, Ross Lagervall from, I'll get that right someday, from Citrix. Thank you, Ross.
Hello. So today I'm going to be talking about the state of live patching in the Xen hypervisor. So this is a project that I did with Conrad from Oracle. So the high-level view is that we've got support for live patching in Xen 4.7, and it was extended in 4.8 to support ARM in addition to x86. So the first question that you might ask is, what's the point of live patching in Xen when we've got live migration support already? Now, there are a few reasons for this. For start, you might be using a VM that's using a pass-through device like a network card or a GPU, and this is tied to the hardware itself, so it's not possible to live migrate that. Also, some VMs might have sort of semi-real-time constraints. They can't take the sort of second or so of downtime that you might get with live migration. There are also some VMs, so you might have a terabyte-sized VM that just doesn't fit on any other host in the system. And if you're a cloud provider, you generally want to avoid downtime as much as possible. If you've got 10,000 VMs, 10,000 hosts, and you want to, each of them takes 15 minutes to patch and boot, then that's a lot of sort of CPU or computing time that's just wasted. So I think all of these mean that it's good to support live patching in addition to live migration. So if we look at the basics of what we're doing, it could be possible to do inline replacement of hypervisor code, so just overwriting existing code and memory with some new code. The problem is that we usually want to use this for security issues, and security issues tend to add an extra check or something, in which case the function would get longer and then wouldn't fit in place of the old one. So the approach we take is to insert a trampoline into the old function, which then allows you to jump from the old function to the new function, which is like a replacement function. So it means that the live patching that we have is sort of function level granularity, so the smallest thing we can patch is a function. So this is just like Linux live patching. So we talk about payloads in the Xen hypervisor, in live patching with Xen. So it's kind of a set of replacement functions that together make the live patch, with the metadata which describes which functions need to be replaced with what. It's packaged in a relocatable ELF file, just like a kernel module, and just like a kernel module, it has symbols that need to be resolved. So the approach we took was to add a simple sort of linker into Xen to resolve those symbols at runtime. We took this approach because Xen already has sort of symbol tables built into it and can access them. And it just seems simpler to do all the module loading in one place in the hypervisor. So to complete the module loading, then we implemented support for performing relocations, applying alternative instructions, and all the other things that, say, is done for Linux kernel module loading. So this was very much inspired by the Linux kernel module loader. It's useful to be able to apply multiple payloads or live patches onto a hypervisor. So if you take the security example, if you have a security flaw that you patch 1 week and then 2 weeks later another one comes out, it's useful to be able to apply a live patch on top, so one live patch on top of another live patch. The problem is that they depend completely on the hypervisor's internal ABI. So if you're accessing offset to structs or calling other functions, it just depends completely on that ABI. And Xen's ABI is not stable, so the approach that we took to resolve this is to embed a build ID in each hypervisor and live patch. This is like a checksum of the binary contents of it. And each payload then is allowed to, at build time, you say on which build ID it needs to be applied. This then creates a model where you have a stack of live patches, and at the base is the original hypervisor. So this is how we allow applying multiple payloads. It's not the most flexible of models, and we could consider changing it in the future, but this is what we've got for the moment.
Does this mean that when you apply a patch, that the build ID of the patch replaces the build ID of the base system that was running before?
Can you repeat the question, please? So does it replace the build ID of the original hypervisor if you load a new patch? No, it doesn't, but you always apply a patch. When you look at it, you look at the last build ID sort of at the top of the stack. So in effect, it kind of does, but they're all still available. So once a payload is loaded in memory, it still needs to be applied for it to actually take effect. So the approach that we take, because we don't want to modify code while it's being executed, is to effectively quiesce the system or pause it. So we have one CPU that does the patching work and all the other CPUs are temporarily stopped. We do this by checking for any live patches that need to be applied in the path where the hypervisor is about to exit to start running the guest. We do this because at that point it basically discards its stack. So there are no functions that could be in use at the time. The only functions that could be in use are the patching functions, and so this is just a small subset of functions that are known to be not patchable. So this avoids having to check for any functions that are in use, which is what some of the approaches for Linux live patching does. So if we're looking at the application process in more detail, the first CPU to arrive at the patching code we designate as the master, and it then just waits for all the other CPUs to arrive. Once they arrive, all the CPUs disable X, just so you don't get any interruptions, and execute other functions. And so those CPUs then just spin and wait for the patching to complete. The master then disables the write protection bit so it can modify code in memory. It runs some hook functions, which I'll talk about later. But then for each function that needs to be replaced, we calculate the offset in memory between the existing function and the new function. Save the first 5 bytes of the old function in memory somewhere else, and write a 32-bit relocate relative jump into the beginning of the old function, which directs it straight to the new function. So this basically allows us to avoid having to modify all the callers of the old function. So if you just replace a function, the only thing that you're changing is basically like a pointer at the beginning of the old function. After all the functions are done, we re-enable write protection, flush the CPU cache because we've modified the executable code, and re-enable X. This then signals to the slaves that the patching is complete, and they do the same. So this whole process usually takes just a few microseconds, so it doesn't really interrupt the system at all. Scheduling latency is usually more than that. If you need to revert a live patch, which is possible to do, the same thing happens, but instead of writing a jump, you just restore the stashed 5 bytes that you stashed when you were applying the patch in the first place. So we also had to then extend the hypervisor interface to allow applying live patches. So there's a new few sub-ops for one of the hypercores, which is like Xen's system call, for uploading payloads, listing payloads, and querying their state, and applying and reverting and all the operations that you want to do. And they're controllable through XSMs, so you can control who is able to do what, although by default it's just DOMZO can do everything and no other domains can do anything else. We've got a tool for also accessing this functionality, which comes with Xen, and it's just available through libxc. So if you look at, compared with the way that Linux live patching is done, this is very similar to the K-patch model, where it basically runs stock machine in Linux and all the CPUs are paused and then it does the patching. The difference there is that it has to check stacks because there can be hundreds of processes in the system all executing code at different points, and functions may be in use, and it's not really possible to patch a function that's in use or safe. But because of the way that we do the patching in Xen, we don't need to do the stack checking, which reduces the complexity. Also, for VMs, latency is not super critical, so we don't use the K-graft model, which is where there's no stop machine or temporary pause. Each patch is moved between the old world and the new world individually. So each process is moved between the old world and the new world individually when it exits to user space. But we just didn't need this complexity. We don't have any ftrace infrastructure or profiling sort of calls in Xen, so we just overwrite the start of the function instead. The advantage of this is that there's minimal overhead, it's just a jump, whereas for Linux it has to call into the ftrace infrastructure, then look up the handler, and only then redirect it to the new function. It also means that we can patch any function basically, rather than only those that are ftraceable, which is usually somewhat less. So that's the hypervisor implementation. The other sort of reasonably complex part is actually building live patches themselves. So it is possible to stick some replacement functions in a file and compile it with the correct options and create a live patch. The main problem is compiler optimizations. So, if you change one function, then GCC is free to inline it, and you don't really know which functions that change will actually end up in. Also, GCC will often copy functions and have different ABIs, so with some parameters held constant, and so this makes it more complex, as well as, say, just changing a macro in a header file, and then you don't know where on earth that might get used, or it's just quite difficult to tell. So the approach we took is to use the unimaginatively titled live patch build tools. So this is based on the K-patch build tool, which was developed by Red Hat for Linux live patching. So this tool's pretty simple to run and pretty quick as well. It takes the source tree from the running version of the hypervisor and the config that was used for it. It also takes the build ID onto which it needs to be applied. So this is what implements the stacked sort of dependency tagging that we had on the hypervisor. And then most importantly, it takes the source code patch, which is the interesting part. So if you look at how it actually builds the live patch, it first does a complete build of Xen to just match the existing build of Xen that's currently running on some host somewhere. We then apply the source code patch and build Xen again with a magic GCC option to split each function into its own elf section, which makes comparing the object files a lot easier in the future. We then revert the source patch and build Xen again with the same option. And each time we do this, we use a compiler wrapper to capture which object files have been changed. We then run a diff tool on those changed object files, and that creates the live patch. So if you just go into that diff process in more detail, for each pair of sort of the original and the patched object files, once they're loaded into memory, we have to demangle them a bit, because GCC is somewhat non-deterministic in what it names the optimized functions that it creates in static local variables. So there's some heuristics to demangle these names. The sections and symbols and functions are all then correlated between the two, so things with the same names are basically matched up into sort of pairs. For each of these pairs, we just do a simple so binary comparison to determine if they're the same, or if they're changed, or if they're new. And then for each of those changed functions, they're marked as need to be included, and we recursively include anything new or any changed function that they reference. There's some special logic to handle things like exception tables and bug frames, because we need to include only the relevant portions into the live patch, so only the changed portions basically, so it needs to be split out. It then creates some metadata which the hypervisor uses for determining which functions need to be replaced. So this is how it iterates through that list. We then write out an elf file, and for each of those diff elf files, we link them all together into a relocatable module, which kind of looks like a Linux kernel module, and that's what gets loaded into the hypervisor. There's some trickiness resolving handling live patches with data. So if a live patch creates new say global or static data or read-only data like strings, this is just easy, it's included in the live patch and everything's handled correctly. If you try and change the initialization of data, or you change the format of the data structure, it's really difficult to, there's no sort of automatic way of creating a live patch for this, so the tool just prevents you from doing that. So the approach that we took instead is to allow hook functions to be executed while the patch is being applied. So this allows you to sort of dynamically transform data, so you can iterate over the listed domains and do whatever transformation is needed, or you can do sort of once-off initializations. We also have shadow variables, which is kind of like a way of attaching a data or some sort of data structure to an existing address in memory, but the new data structure or member variable is stored in a separate hash table, and so it's kind of a way of attaching a new member to an existing data structure. But this then needs to be done in the hook functions, or we might need to modify the patch somewhat. In some cases, it's also possible to rewrite the patch in such a way that it doesn't actually need to use a new data member, because mostly when patches are written, they're not sort of written with consideration of live patching in mind, but it's often possible to do that. we compare this with Linux live patching, they have general purpose modules, and the patching mechanism sort of tries to hook into that at various points. But this can be a bit tricky, trying to get it to hook into the right points. Because Xen does not support loadable code modules in general, the patching process is quite straightforward, and it integrates quite easily. Not supporting loadable modules also avoids quite a lot of issues, like if you try to patch a module that's not loaded, or if you try and need to patch or reference a symbol that's not exported in a module, all these things sort of create quite a few issues, and it's possible for modules to have the same symbols, and it's difficult to resolve them. So we just sort of sidestep a lot of those issues. Kgraft, as far as I know, does not have a tool to automatically create live patches. They have a tool to diff builds using the dwarf info, I think, and then you're meant to just stick the replacement functions in a file and just build that using the normal kernel module build system. So as far as I know, Kpatch themselves, even though they created this tool that we sort of repurposed for Xen, I believe they're also moving towards not using it for some reason or other, because as far as I can tell, it's still a lot easier than creating this by hand. So that's kind of where we're up to. As far as future work, there's an issue at the moment with handling NMRs and MCEs during that critical patching region. So at the moment they're just ignored, but we want to change it so that they're recorded and then replayed after the critical section is left. But hopefully there's a very low chance that you hit an NMR in that couple of microseconds. So we also want to add support for assigning payloads. So this would make it more difficult to accidentally or intentionally load a malicious payload, especially if you sort of consider the sort of vendor distribution scenario. So I've got some patches to do that I currently need to send out. Then finally, I think we want to remove the experimental tag in Xen and sort of declare it as a supported feature. So part of this work is adding it to the upstream OSS sort of testing infrastructure. There's some patches on the list to do that, but I don't think they're complete yet. But I think once that happens, then we'll be sort of prepared to call it supported and kind of done. So that's pretty much the state of where we are. If there are any questions, I think we've got a minute or two. Otherwise, feel free to find me at the Xen booth. I've got a demo of it running, so you can sit there.
Since does that mean if I have a system running Xen to create the live patch exact same
Yes, if you want to create a live patch, you do need to have the same tool chain, basically an identical build system. So, I mean, generally, if you're using Mock or something like that to build it, it's pretty straightforward. Any other questions? All right, thank you very much.